We're human motion synthesis through style transfer. I'm Amal.
I'm Sid.
I'm Kunal. I'm Rohit.
So our project is focused on motion synthesis, and motion synthesis is the act of generating realistic human motion and animation. And so if you look at the image on the right, that kind of summarizes how motion synthesis in general works. You take a large amount of recorded motion data, which is mostly comprised of joint data over time steps, so the poses of each joint over every frame of the video. And then you pass it in through whatever model you choose, and your output should be a completely new generated motion that is based on the multitudes of motions that was passed in. And the important thing about this is that it's generating a brand new motion. And so there's a couple existing models of motion synthesis. There's statistical models, which try to get motion that is statistically similar to the inputs. There are GAN models, which take in the large amounts of data and then generate the new motion. And then what we focus on is style transfer. And so the reason style transfer is unique is that it is trained on a large amount of data, but your end result is a model that takes in two inputs and generates a brand new motion based on those two inputs. And so because of this, you can retain the individual style characteristics of those two inputs, whereas the previous models would kind of wash out some of the style elements since they take in the large amounts of data and output one motion. And so we have a couple hypotheses regarding style transfer. We believe that motion synthesis through style transfer creates identifiable motion, meaning that if I pass in a certain style into the style model, we should be able to identify which style was used to create that. And humans will react differently to different styles of characters. And so we had a couple goals in creating accurate style transfer. So relating to our first hypothesis, we want to create identifiable motion through style transfer. This being that if one of our inputs into the style transfer is like a sad motion, a human participant should be able to watch that video and recognize that there are sad elements in that motion. And second, we want to use style transfer to create lots of motion. And so what this means is that style transfer takes in two inputs. We want one of our inputs to be the physical motion that the human takes through the environment, and then we want the other input to be the style. So for example, the physical motion would be a right turning motion through the environment, and the style motion would be an angry style. And when this goes through our style transfer model, this would create an angry right turn. And because of this, we can create a lot of different types of motion. So we only need to record one right turn motion, and we can record as many style motions as we want, and create as many stylistic right turns as we want. So like you can create angry right turns, sad right turns, a multitude of other right turns just by recording one right turn. And so to do this, we decided that like our best option was the Averman model because of the focus that they have on content motions and style motions. Content motion is kind of like the physical motion that the character takes through the environment, while style motion would be like angry, sad, this type of style that I mentioned before. And so I can walk through this motion pretty quickly. So the style motion, you take the inputs of the joint data that gets passed in through an encoder. This specific model uses a 2D encoder, but we don't need that, so we're mostly focused on the 3D encoder since all the joint data is in 3D form. And that creates a style code, which is passed through a perceptron layer. The content motion follows the same steps through an encoder, creates a content code. Both of these are passed in as inputs to the decoder, which outputs our final motion, our synthesized motion. And from this, we can calculate our adversarial loss, which tells you how well our model performed in creating the motion.
So we've already talked about how the Averman model works, and the way it works is it uses an existing data set, being the CMU motion capture data set. But there's a key difference between that data set and the data we have at our lab here at UT. Primarily that the CMU mocap data set has over 30 joints in their skeleton, whereas both in the VR trackers and the Azure Connect, we only have access to around 20 joints. And this proposes a big problem, as to run the model, we need to have a consistent amount of joints both in the training set and in like the test motion that we pass in to produce the style output. So we had to retarget the skeleton in all of the CMU mocap the CMU mocap data set, and we have to eliminate certain joints. And we had to update like many config files in the model to support the like reduction from the 30 joints to the 20 joints. So then our goal remained to set up a pipeline that was capable of using the BWI Labs VR setup with the Averman model. And initially we had a difficulty in tracking joints using the VR trackers, so we then proceeded to use the Connect, which we'll talk about in a bit. But we were able to successfully retarget the data set and able to retrain the model with the new data set.
Okay, so like Sid said before, we kind of moved into Azure Connect just because the VR system data, positions and rotations were, it was hard to extract data from it, so we just moved into Azure Connect. One quick aside, the BVH file, which is the file supported by the model, is interesting in the way that supports the data, right? So it doesn't actually contain any position data except for the root, which are the hips in this case, but it contains offsets, which are basically bone lengths, and then rotation matrices, which are used to, both of them are used to calculate the positions of each joint. So from like the hips and the offset, you can basically get position data for each joint. And so the position data from the Azure Connect was basically unneeded, and so we just kind of used the rotation matrices and offsets. One other thing for the Azure Connect is the joint data is local to the joint itself. I'll talk about that in the next slide. Yeah. So these two images, this one is for the VBH file format, and you can see that basically there's one global coordinate system. Every coordinate system is the exact same in each joint, but then on the Azure Connect, they're kind of local to the joint itself, so they're moved around to support the joint. And so we had a really, really difficult task of basically translating all these local coordinate systems into a singular global coordinate system. And initially, we thought it wasn't that big of a deal. Turned to be a pretty big deal. So initially, you can see that like on this arm and on this arm, it's just like one axis that was flipped. And so we thought, you know, just reverse it. It's not that big of a deal. But then as you're moving from like the arm to the leg, like the entire coordinate system rotates. And so there was a lot of rotation computation that was needed. We're still working on it right now to change this entire coordinate system into one global coordinate system. And then if we have all of these, even though they're not the same as this one, if we have them all the same, we can translate each joint to map to this one. And it's the same. It's going to be the same one. And that's what we're working on right now. We're not quite there yet, though.
So, though we're still working on the Connect, we do have results from our VR trackers. One thing to notice, though, is that lesser joints does yield a lesser accuracy, and that's just in general because with more joints you get more data. And what we did is we started our training from scratch, initially synthesizing like in-human motion, nothing that looked like what a human would look like. The process takes a total of 8 hours, and in the end we could produce stylized motion on top of a base content motion, where content motion can be like walking, strutting, things that Amal already mentioned. It does only work for some styles right now, as some styles are just inherently not compatible with each other. Imagine putting like an angry and a sad style on top. Like with a angry style overlaid on a sad base motion, it just wouldn't produce good output. And the one thing we noticed is that with short clips, we'd actually have a higher accuracy. So like larger mocap files would yield like invariable motion, and it wouldn't be as smooth. And in general, we had a model loss, which was measured through adversarial loss. But then when we ran the data over like our own base content motion, we get a loss an error known as Jacobian inverse kinematic error, which basically aggregates loss over joint positions. So this metric was actually more useful for telling if our motion was like human or not. We'll see on like the next slides what I mean by that. So here's an example of a base motion, which would just be a base strutting motion, and then a stylized motion, which you can see his this is an example of an old stylized motion, and you can see like his back is arched over. So then when we combine the two, moves very fast, so I'm going to slow it down. You can notice that it took the initial content motion, which was the strutting and turning right, and it overlaid the old style by just arching it back over as it would turn right. So it is able to produce output like that. You will notice that it's a pretty short clip, but we had some, like in general, like long clips are not very accurate. So here's an example of another accurate output. I believe this was the happy plus strutting output. And then you can see that when we have a longer clip, with the middle, the highlighted image being the output, it does a very interesting dance-like motion. And what's actually funny is that this this combination of style, it didn't have jumping at all. It just like randomly started jumping. So in general, like longer clips produce pretty inaccurate output.
Yeah, and so going forward from this, we have a proper model that's able to, in a lot of cases, generate proper realistic human motion. And so the goal is to integrate this into lab research and doing stuff with VR. And so, we talked initially about how humans will react differently to different motions, based on the style. And this model is able to generate motion of different categories. It's able to walk, it's able to turn, and that's all kind of stuff that's trained on from the CMU database. And so one thing that you could very well do is just some kind of a motion planner where you just generate VR motion over time, and combining lots of different clips together to generate some VR human path. The thing that we kind of focused on at the very beginning was about people being able to tell different motions apart. If something is angry versus sad, you should be able to tell that. And similarly, like if you can integrate someone eventually into that style through the Connect, and so you should be able to tell that this is this person, this is the other person. And ideally, you'd also want to be able to tell, and you want it to be so good that you couldn't necessarily differentiate a lot between if it's just a basic person walking in VR versus if it's a VR generated agent. And so that's kind of an experiment to set up to see if, one, people can tell between different human stylized agents based on humans, and if you have an agent and a human, can you tell, is it difficult to tell which is which? So just go next slide. Yeah, so this is just kind of going over that, where you provide 3 base motions and apply those as styles up on a variety of base motions that do different basic movements, and then ask a bunch of participants to tell if they can tell who is who, if they give them the references of the person. And if it's a good model, then you'd actually be able to tell that it's that person. And if that's possible, then within any kind of lab research or in video games, you could really easily just create a bunch of base motions and then have short clips of a person doing some their basic human motion, and apply that over, and you get distinct motion where you can tell there are lots of different unique people, and it's not just generic VR agents within this environment. And so overall, just we found that using stylized using style transfer for VR human motion generation is a pretty effective method that retains individual characteristics of the style and also the base of what it's doing. And going forward, we're going to try and get the Connect working so we can input our own custom data into that. And it is just also a simpler setup than hooking up lots of VR recording devices to put yourself into this model. So we're going to integrate this into the lab and see what happens. All right, so we'll take any questions. Thank you.
All right, so questions? Go for it.
Have you all looked at GANs at all? Have you done any research into?
This technically is a GAN.
Oh, it is, okay.
Yeah.
Nice.
Yeah, so by base motion, do you just mean walking, or what if you try more, or how about more complicated motions like dancing? Because people have different styles when it comes to different things like that.
Yeah, we've for now we've mostly focused on walking because like we want to do like a hallway passing experiment where the VR avatar is walking, so we mostly focused on that. I think we probably could support like running at least. I don't know about dancing and complicated motions like that.
Yeah, I mean, like in the CMU data set, like it does label like lots of different categories. There's like so there's like 20. I forget how many exactly it is, but there's like a bunch of categories that the BVH files are listed as. Like if it's a 0-1, it's walking. If it's like 0-3, it's like it's a right turn or a left turn or it's jumping. And so like we didn't really include those here, but like in those motions you can kind of have a variety. Dancing is not there. Unless you include the bad model.